All right, this is going to be the first of 2 videos on chapter 15. All right, so equilibrium happens when the rate of the forward reaction is equal to the rate of the reverse. Now, you must have a reversible reaction in order to be at equilibrium because we have to have both a forward and a reverse rate. So if we would look at this particular equation, the rate of the forward would be equal to K times the concentration of the reactants. And then for the reverse rate, it was rate equals K times the products because it's going in reverse, so these would be the reactants now. And since this has a coefficient of 2, we're going to make that squared, even though we didn't do that before when we did rate laws. All right, so if at equilibrium the rate of the forward is equal to the rate of the reverse, then that means K of the forward is equal to K of the reverse. And if we wanted a ratio of the forward to the reverse, we would have the product over the reactants, and that would be equal to a constant, which is the equilibrium constant, capital K. So let's say we have a reaction that looks like this. So my equilibrium expression, and this one is for concentrations, meaning we're going to be using molarities, would be D, because we're doing products over reactants, D to the D power, E to the E power, over reactants, A to the A power, B to the B power. And if we're using pressures, it looks very similar. The only difference is instead of Kc, I call it Kp for pressures, and we use rounded parentheses instead of the brackets. The brackets are used for concentrations, molarities, whereas if we have pressures, we use P. So P of whatever D is. So they look very similar. All right, so if this is my equation now, we would do products NH3 squared over H2 cubed times N2. And there isn't anything in here. This is like a multiply sign, so they're not added or anything. It's just you would multiply the bottom one. And the cubed just goes to the H2. And if we're going to be using concentrations, it would be Kc. All right, if this is my expression, then we would have, this should be reversible, not just backwards arrow, so it should be reversible, but products O2 cubed over reactants O3 squared. Now, if we wanted to convert Kc to Kp, because sometimes they'll give me a Kp, but I need a Kc or vice versa, we're going to use Kp equals Kc times RT, and the product of RT is to the delta N power. And delta N is the moles of products, gaseous products, minus the moles of gaseous reactants. So we'll have an example. So if that's my equation, and again, that should be reversible, they give me Kc. If I wanted to calculate Kp, Kp is equal to Kc RT to the delta N. So they gave me Kc, which I'm going to plug in. R is still our ideal gas law constant, 0.0821. Here they're using 0.08206. Temperature should be in Kelvin, so 300 plus 273. And then my delta N, I would take 2 moles of my products minus 3 plus 1 is 4 moles of reactants. So 2 minus 4 gets me -2. So I would multiply those to the -2 power times this, and I should get 4.34 times 10 to the -3rd. And there is not a label on K, the equilibrium constant K. So what does K tell us? So if K is really, really big, then that means that the numerator, meaning the products, are much bigger than the reactants. So in that way, it says that the reaction favors the products because the forward rate is happening faster than the reverse rate. Another way that it is said is that the products predominate, meaning there are more products than reactants. And if K is really, really small, then it favors the reactants because the denominator is bigger, and then the reactants predominate. Now, when we say greater than 1 and less than 1, like we're talking huge numbers, meaning like probably greater than 1,000. And if we're saying less than 1, we mean like 0.001. So really, really small numbers. And when we say K is at equilibrium, K is 1. And we say it's about 1, anywhere from like 1/1000th to 1,000 is about what 1 is. All right, sometimes our reaction will change. So like if this is my initial reaction and I know what K is for that, the equilibrium constant, what if my equation becomes doubled or reversed or cut in third? What would happen to my K? So for this particular reaction, they gave me K, and K is 0.212. Well, what if, and they wrote the expression here, NO2 squared over N2O4. Well, what if this reaction is reversed? Because now the N2O4 is on this side and the 2 NO2s on this side. So if it is reversed, then I take it to the -1 power. So I would take 0.212 to the -1 power, and that would give me my answer. Whatever I do to my K or my equation, whatever I do to my equation, I do to the power of K. So if I were going to, in this case, double my equation, then I would have to take it squared. So I'd take my original K and I would square it. Let's say my equation was tripled, then I'd have to take it to the third power. Let's say it was reversed and cut in half, then I would have to take it to the -1/2 power. So a half for being halved, negative for being reversed. So whatever you do to your equation, you do to the power of K. Now, we sometimes see homogeneous reactions. In that case, all of the reactants and products are in the same phase. But sometimes you're going to see heterogeneous ones where they're not all in the same phase. And as long as you have gases and things that are aqueous, those appear in your equilibrium expression. But if you have any solids or any liquids, they do not appear in the expression. They just have a value of 1 and they're not included. So if this is my equation, we can see this is a solid, and this is a gas. So this one isn't going to appear, this one's not going to appear. The only one I'm going to have in there is this one. So if I do the product, CO2, over the reactants, there aren't any. So that means it would just be K equals the concentration of CO2, or if you're doing Kp, your K is equal to the pressure of CO2. All right, so back to our equation for the Haber process. And again, this is supposed to be reversible. I would write my expression, so NH3 squared over H2 cubed times N2. If we know our equilibrium concentrations that they have given me here, I just plug those concentrations into my expression, and that will give me my equilibrium constant.